Okay, good morning. We're now at the end of a long semester. So today is hopefully the last lecture where we can sort of wrap up the material on control. So what I'd like to do today is, so we talked about the basics of control, robot control last time. Today we're not going to go much farther beyond that. Rather, what we're going to do is we're going to go back and fill in some of the details, and maybe they may have some gaps last time. So we're going to fill in all that stuff, and then conclude with some general comments on arbitrary control of general N-link robots. Okay, so you know the condition of my voice is not very good today. It's been a hard semester. You guys have been tough on me, so bear with me. We'll try to get through. Okay, so last time we started by looking at the mass spring damper system. Okay, the governing equations were of the following form. Okay, so you can imagine some mass m attached by a spring to some stationary wall. Okay, and x represents the position of this mass. Okay, and k is a spring constant, and b here reflects friction. Okay. All right, so we took as a something as a sort of a benchmark system, this mass spring damper system. Okay, and the first thing we did was try to write down the solution in the case that f equals 0. All right, so we didn't have to do this, but just to sort of touch base with the matrix exponential material that we've been using throughout the class. Okay, we made this definition, define x1 to be x and x2 to be x dot. And with this definition, we can now rewrite this equation in the following way. So ddt of x1, x2 is equal to 0, 1, x1, x2. Okay, and this is minus k over m. This is minus b over m. Okay, plus 0, 1 over, 1 over, oh, sorry. That's correct, yeah, 1 over m f. Okay, so we can rewrite that second order differential equation into a first order system, first order linear ordinary differential equation. Okay, so f here is the input. Okay, so this is our control. And x1, x2, okay, this is our state. Okay. And the goal that we set for ourselves was, given some arbitrary initial values for x0 and x dot 0, okay, or using our x1, x2 notation, or x1, 0, x2, 0. Okay, we want to find the control. Okay, find our input f that drives. Okay, that makes system come to rest at x equals 0. Okay, make it go to its equilibrium position. So when I say come to rest, that implies that it goes there and it stays there. Okay, so the velocities have and accelerations have also must also be 0. Okay, as fast as possible. Okay, so it's a simple goal. You know, it's also a pretty practical goal, right? You know, if you imagine this to be a robot doing some task, you want it to do it quickly. Okay. All right. Now, before jumping into the solution, let's think about this problem intuitively. Okay. So here's an example from, well, it should not be everyday life, but probably some of you have tried it, right? So you're driving. The light turns yellow. So what do? You accelerate, right? Try to beat the light as fast as you can. And if you're lucky, you'll pass it. If you're not lucky, it turns red. What do? You slam on the brake, right? And you pray, oh, I hope I stop before I go into the intersection, right? So that's a good strategy, right? If you think about it. It's kind of like this, right? So the mass is the car, right? And you're trying to make it come to rest at this certain position as fast as possible. So intuitively what you do is you accelerate as fast as possible and then brake, okay, as strongly as possible. Okay? So intuitively, you would expect something like and of course, it depends on, right, initially how fast you're going, things like that. So as soon as you see that light turn yellow, what do? You floor it, okay, maximum acceleration. And then as soon as the light turns red, you do maximum deceleration. Okay? So this is like a maximum, and this is where you hit the minimum. Okay, for those of you who've tried this, it's guesswork, right? Sometimes you just make it, sometimes you go over. Okay, so you know, I recommend you don't do this too often, or don't do it actually. It's the same situation for this problem, right? In order to make this really work, okay, to execute properly, okay, we need to know the exact values, okay, of the model parameters. Need to know, for example, M, B, K exactly. Okay. But we don't. Typically we don't. Okay, and there may be other effects in there that are not captured by the model, right? There might be unmodeled dynamics. Okay, so it's not reliable. Okay, and we don't. Okay, what else happens? Okay, so if you're driving like me an ordinary car, okay, you know, maximum acceleration is about here. Okay, if you drive one of the sports cars that our students like to drive these days, maximum acceleration is here. Okay, you know, if your father happens to be somebody named well, we won't get into details, and you drive a Ferrari, that's going to be up here, right? So, in the limit, what happens? In the limit, what happens? This could potentially go to infinity, right? So you're going to have this infinite spike, and you'll go really fast. And over here, you have this infinite spike in the other direction. Okay, bring you to a complete stop. So most cars don't have, well, cars don't have infinite acceleration capabilities, right? There's a limit. Okay, it's the same thing with motors. Motors have limits. Okay, actuators saturate, and you know it's not a good idea to have the actuator saturate all the time, to spin it at a maximum rate in one direction and the maximum rate in the other direction. You know, it puts a lot of wear on the motor. Okay, so so this kind of strategy causes actuator saturation. Okay, and not always desirable. Okay, especially if you're going to be doing this repeatedly. Okay, so for these reasons, we decided to look at a different kind of control. Okay. We looked at a control law of the form F equals minus kpx minus kd x dot. Okay, so x and x dot, okay, x dot are assumed to be available as measurements from sensors. Okay, can be measured using sensors. Okay, and we have to pick Kp and Kd. All right? Okay, so if we use this kind of control, let's see how the equation behaves. Okay, then we have, all right, so mx2 dot plus bx dot plus kx equals minus kpx minus kd x dot, right? And if you just clean this up a little bit, b plus kd x dot plus k plus kpx, okay, this equals 0. And we looked at solutions to this. Okay, so let's call this, say, b prime. Let's call this k prime. Okay, so if you plot the solution, okay, as a function of time, here's t. Here is x of t. Remember, we want to make this go to 0, right? So let's say it starts up here, for example, somewhere. In the best case, this graph goes exponentially toward the origin, eventually approaching 0 as t goes to infinity. Okay, so we achieve this best case when, let's use a different color, when this is, when b prime, let me see, I always forget, b prime squared, right, b prime squared equals 4m k prime. Okay? And this is the we call this the critical damping case. Okay. Now, if B prime happens to be bigger than 4mk prime, the graph looks something like that. Okay, so this is B prime squared greater than 4mk prime. Okay, and this is the overdamped case. Okay, finally, when B prime squared is less than 4mk, we have something like this happening. Okay, so this is the case when B prime, as I said, is less than 4mk prime, B prime squared. And this is the underdamped case. There's not enough damping, so there's oscillation. Okay, so if possible, we want to choose, okay, try to choose, so what do you choose? Kp and Kv, right? Kp, Kv, okay, to achieve critical damping, because that's the best case. Okay, so is this possible? Well, remember here, we said that we don't know the exact values for M, B, and K. Okay? Because if we did, we wouldn't have to do this, right? So you try. Okay? Might have to do some experiments, some little tuning. Okay? But you try to achieve this critical damping. You may not always get it. Okay? But here's an important point. Important point is that whatever you choose, okay, whatever you choose, as long as these things are positive, okay, eventually it's going to go to 0. Okay? It may take a long time, or it might overshoot, but eventually it'll go to 0. Okay? So even if you do a bad job of choosing Kp and Kv, just using this control law, okay? Sorry, this is Kd. Okay? Using this control law will guarantee, ensure that you will get to x equals 0. Okay? Even if you don't know the values of M, B, and K. Okay? Okay? In the limit, even if M, B, K are not null. Exactly. Okay, and this is a good thing. Okay, we want a controller that will do the job, even when there are uncertainties in the model.